Hello and welcome to the Math Kangaroo 2024 video. My name is Navya Sreeraj and I will be taking you through the questions for grades 5 and 6 for the Math Kangaroo 2023 test. So a little bit more about this Math Kangaroo competition. So Math Kangaroo is a test that mainly uses math but a bit more logic. So you have to really carefully look at the questions because there might be a few trick questions. This test is comprised of 30 problems split up into 3 parts. 3-point questions, which are pretty easy, 4-point questions, which get slightly harder, and 5-point questions, which are the hardest. So it really depends on how you study and how you work, but personally, I would recommend for this test to start off with the 5-point questions, just because the 5-point questions are the ones that normally take the most amount of brain power, and especially by the end of the test, if you're a little bit tired and your brain's a little bit tired, it would be easier if you did the 3-point questions. But let's get going. So the first question, Holger writes the numbers up to 40 in the table in the same way as shown. Which of the pieces from A to E can he then cut from the table? So we have our table here, and we're going to choose a really cute color, turquoise, and I will have my very nice looking cursor helping me out. So we are looking at this table, and we can see that it's going in normal ascending order. And we know that they start off with the tile 12. So we know that the top tile will be 12 right up here. And when we follow the shape of the different options, we know that the shape will roughly look like this. So what we need to do is we just need to fill in all the numbers in this table. I'll choose black. And we go up from 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. So by the time we're done with the third row, we can see that we can already take off some of the options. So for these two boxes, 20 and 21, we can see that some of the options do not fit. Like A does not fit, D does not fit, and E does not fit. But currently we need to choose between B and C. So we still need to keep going. So go from 25, 26, 27, 28, 29, and we can stop right about there because we can see that our entire turquoise box has been filled. So as we're looking at our options, which are currently just B and C, we see that the only one that has 29 in its bottommost square is C. So the answer for this question would be C. Thank you. Question number 2. Matchsticks are arranged to form numbers as shown. To form the number 15, one needs 7 matchsticks. To form the number 8, one needs the same amount. What is the biggest number that one can build using 7 matchsticks? So I got a really cute flame cursor for this problem. And we see that we have all the numbers, let's choose red, over here. So we have 0, 1, 2, 3, 4, 5, 6, all the way up till 9. And we're going to write down how many matchsticks each number needs. So for 0, you would need 1, 2, 3, 4, 5, 6 matchsticks. For 1, you would need 2 matchsticks. For 2, you would need 1, 2, 3, 4, 5 matchsticks. For 3, you would need 1, 2, 3, 4, 5 matchsticks. For 4, you would need 1, 2, 3, 4 matchsticks. For 5, you would need 1, 2, 3, 4, 5 matchsticks. For 6, you would need 1, 2, 3, 4, 5, 6 matchsticks. For 7, you would need 3 matchsticks. For 8, you would need 1, 2, 3, 4, 5, 6, 7 matchsticks. And for 9, you would need 1, 2, 3, 4, 5, 6 matchsticks. And now we need to know what is the biggest number one can get from using 7 matchsticks. So we can go from our options right now. So we see that we have 31, 51, 74, 711, and 800 as our options. So it's asking for the biggest number. So let's start in the biggest number in our options, which is 800. So for 800, there is 1 8 and 2 zeros. So 1 8 uses 7 matchsticks. 1 0 uses, this is for 800, 6 matchsticks. And 1 0 uses 6 matchsticks. And that is way more than 7. It would be 19 matchsticks. So it's no way that it's letter E. So let's go to 711. So for this one, number 7 uses 3 matchsticks, 1 uses 2 matchsticks, and 1 uses 2 matchsticks. So for this one, we can see that 3 plus 2, which is 5, plus 2 is 7 matchsticks. And since we're going from the highest to smallest, 711 would be the biggest number that would use only 7 matchsticks. So the answer for number 2 is D. Question number 3. Which of the shapes cannot be split into 2 triangles using a single straight line? Okay, I'm going to underline a few of the important parts of this problem. So it says cannot, that's already underlined for me, and we need 2 triangles using a single straight line. So as we look at all of these shapes, we're going to go through them and see whether they can be split up using a single straight line. So for A, we're going to try and split it with a straight line. But I don't think we can split it using just one line into triangles. But we're going to keep going and see how the other options work out. So for B, we're going to try and split it into 2 triangles. You go from corner to corner, and we see that we have 1 and 2 triangles. Same thing for C, we go from corner to corner, and we have 1, 2 triangles. For D, it's already a triangle, but you can make it into 2 triangles by splitting it down the center. Got 1 triangle here and a second triangle here. And E is a square. We could just go corner to corner and we get 2 triangles. So for this one, the only one that you cannot split into 2 triangles by using just 1 straight line is A. So the answer for number 3 is A. Number 4. Emily has a piece of paper marked as shown. When she folds to form a cube, which of the following 5 cubes can she get from this paper? So this is one of the more logic-oriented problems for Math Kangaroo, and you kind of have to visualize it. So we see that she has these 5 cubes, and we need to see which one is possible. So let's start with A. So A has 2 yellow, so these 2 tiny figures are kangaroos, just to let you know. And we see that A has 2 kangaroos with their heads together. So we're going to see how we could fold this piece of paper to look like a cube. So for this, we would just fold up these sides, and then we would have to fold this twice. And then you would have a cube kind of with the green on the bottom and the green on the top. But because this is a logic problem, you can kind of tell that they're flipping the cube around. So you're not totally sure which one's exactly on the bottom. So when we look at A, we see that these 2 kangaroos have their heads together. But when we look at the 2 adjacent yellow squares, we see that this front of the kangaroo is adjacent to the head of the kangaroo. So there's no way that you could get A as a cube. So we're going to cross that out. next we're gonna go on to B. So for B, we see that there is a blue kangaroo cube and a yellow kangaroo cube right next to each other. So for this one, we have the tail of the blue kangaroo adjacent to the tail of the yellow kangaroo. But when you really visualize it and when they fold it up, the yellow kangaroo and the blue kangaroo will be kind of like flipped upside down. The only thing that they will share is their tail. So when we look at B, and we can also tell that the top would be green. You just kind of have to visualize it. And when we look at B, these two tails are together, and we can also see that green is on the top. So B is definitely possible, and the answer for this question is B. Thank you. Problem number 5. 9 steps of a staircase arranged in a cylindrical order starting from the bottom and leading all the way to the top can be seen. All the steps are equally high. How many steps cannot be seen? So for this problem, I'm going to need help. So I have called my friend Bob to help me out. This is Bob. And he's telling me that there are steps that I need to count on the other side that I cannot see. So we're going to color it in on this side of the grid to kind of show which steps we can't see. So we know the steps are diagonal to each other, so on the other side there would be this step that we can't see, this one, this one, this one, this one, and then we see the steps wrap back around, and then we keep going. This one, this one, this one, this one, and a half of a step, the same thing that we did on the top, and they wrap back around. So I get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 steps. Oh, Bob's saying something. He's telling me that there are steps on the side of the cylinder that I can't see, but he can see them. But I can kind of tell that there are steps because when you look over here and over here, we see that there is one staircase step that's missing. So the only possibility is that Bob can see these, but I can't because I'm not on the side of the cylinder. So Bob tells me that there's 2 steps that I'm missing. So we take 10 steps and then we add the 2 steps that I can't see, but Bob can see, and we get 12 steps. So the steps that we can't see, there are 12. So the answer for number 5 is D. Number 6. Anna has 5 discs of different sizes. She wants to use 4 of them to build a tower. She always has to place a smaller one on top of a bigger one. How many ways are there for Anna to build a tower? So we have 5 discs over here, and I'm going to underline some of the parts that are really important in this problem. So she wants to use 4 of the discs to build a tower, and she always has to place a smaller one on top of a bigger one. So if she uses 4 of the discs, one of them will be skipped. And as long as we go in ascending order, it should be fine. So one way to do this problem is, I'm going to choose green. I'm going to give all the numbers to these discs. Green's not a good idea. I'll choose black. 1, 2, 3, 4, and 5. So we see all of these discs, and to have them in ascending order, all we need to do is just skip 1. So we could have 1, 2, 3, 4, where we skip 5. So skip 5. We could have 1, 2, 3, 5, where we skip 4. We could have 1, 2, 4, 5, where we skip 3. We could have 1, 3, 4, 5, where we skip 2. And we could have 2, 3, 4, 5, where we skip 1. And other than that, there are no other possibilities that we could have, and that means we have 5 possibilities in which we can stack them while following all the guidelines. So the answer for number 6 is B, 5. Question 7. 4 ribbons M, N, P, and Q are wrapped around a box. In which order were they wrapped around the box? So I have a really cute ribbon cursor for this problem, and we're going to look at this box. So we see that we have M, P, Q, and N. For this problem, what you would do is you would see which ribbon was on top and which one is on the bottom. So if a ribbon's being covered, that means that the ribbon was put on earlier than the ribbon that's covering it. So we're gonna look at the place over here, because that's where 2 ribbons intersect. So we're gonna look at all of these different places, because they tell us which ribbon was put on first and which one was put on last. So when we look at N and where M is, we can see that N is underneath N. So ribbon N was put on before ribbon M. Same with Q and N. We see that ribbon Q is over ribbon N, so we know that Q happened after N and N happened before Q. But we don't have any correlation between P and N. So when we look at P, we can see that P is over on top of M and Q. So that means that P happened after M and Q. So when we look at it, we know that N was one of the first ribbons was the first ribbon that was put on, and P was most probably the last ribbon that was put on, just because it's over M and Q. And then we have to figure out which one was put on before or after, M or Q. So when we look at this intersection right here, we see that M is below Q, which means M was put on before Q. So after N, M was put on, and then Q was put on, and then P. So as we look at all the possibilities, the only one that has N, M, Q, and P is letter D. So the answer to number 7 is letter D. Question number 8. Alice has 4 jigsaw pieces. Which 2 can be fitted together to form a hexagon? So for this one, we're going to look at the options. So when we look at A, it says 1 and 2. So we're going to look at the pieces 1 and 2. So before you think about putting them onto the dot grid to match it up with a hexagon, we need to see that 1 and 2 has a lot of overlapping spots. Like all of this overlaps with all of this. So that basically tells us that it can't be 1 or 2, because there's also a space over here which would not be filled up if we use both of these pieces. So it can't be option A. But moving on, we're going to look at option B, which says 1 and 3. So when we first look at 1 and 3, we can see that they almost fit together, kind of like a jigsaw puzzle. So we're going to draw those in using the dot grid that I wrote in for the hexagon. So 1 looks kind of like this. Just looking at the shape of 1. And 1, I'm going to color it in. So this entire part would be 1. And when we look at 3, we can see that 3 basically fits. But let's still draw it in. I'm going to use blue for this one. So we look at 3, and we're going to draw in how 3 would look for this. And 3 fits perfectly with 1. I'm going to color it in too. So we can see that the answer for this question is B, because 1 and 3 fit perfectly together, and it forms a hexagon. Thank you. Number 9. A dark disc with 3 holes is placed on top of a dial of a watch. See the diagram. Then the disc is rotated around its center. Which numbers can be seen at the same time? So for this problem, I'm going to have my little cute clock cursor to help me out. So what we would first start off with is we were going to write down all the possible circles, numbers that would be shown at the same time. So we already have one of them, which is 1, 5, and 7. And then if we move it over one, we get 2, 6, 8. Move it over one more, 3, 7, 9. Next is 4, 8, 10, 5, 9, 11, 6, 10, 12, 7, 11, not 13, but 1, because this is a watch that only goes up till 12. And then we keep going. 8, 12, 2, 9, 1, 3, 10, 2, 4, 11, 3, 5, and finally 12, 4, 6. So we're going to compare all of those to the different options that we have. So 4, 6, and 12. So let's look at the one that says 4 over here. That one has 4, 8, and 10, so it doesn't work. Let's look at the one that says 6. 6. It has 12, but it doesn't have 4, so it can't be 6. And let's look at 12. For this one, it shows 12, 4, and 6. It has all the options, which means the answer to this problem would be A. Question number 10. Jan sticks these 3 pieces of paper on top of a black circle. Which picture can he not obtain? So one of the biggest keywords here is which picture can he not obtain? This is because, so this means that 4 of these options means they are the ones that he can get, and then 4 of them would be ones that he couldn't get. So let's just start with option A. So we see the pictures, and we know that the green paper is a semicircle. So if it wants to show up over there, the semicircle can be kind of like this. This would be the semicircle. And then we would put these 2 quarter circles over here and here. And this picture could totally be made. So A is not the answer. Moving on. B. So for B, we see like there's a small sliver of the semicircle. So we know that they're underneath the quarter circles. So we could kind of draw it out and say that it looks kind of like this much, right? And then we would take the quarter circles, and we see that the quarter circles are right here and right here. So B could totally be done and is not the answer. C. So we see that there are 2 sides of the quarter circles that have green. But this is not possible, because if you wanted green on this side, then the semicircle would look kind of like this, or at most like this, or like this. But there is no way that they could have the green portion right over here. So it means that C, there is no way that C could be made, so our answer is C. If you try out the rest of the equations, you can also see that those are totally possible with the semicircle and the quarter circles. Number 11. Francesca writes down 3 consecutive 2-digit numbers. They are in increasing order. Instead of the digits, she uses symbols and writes square, diamond, heart triangle, heart square. What does Francesca's next number look like? So for this one, we need to find out some of the similarities with the 3 consecutive numbers. So something that we see is that the second consecutive number and the third consecutive number both have hearts. And the first consecutive number and the third consecutive number both have squares. So what this basically means is that the second consecutive number and the third consecutive number will have the same tens value. And then that first consecutive number and the third consecutive number will have the same tens place and ones place. So as a random example, let's just assume that the first consecutive number is 29. And then the next one would be 30 and 31. So this is just trying to try it out. So when we look at this, let's try to match it up. So the hearts show over here that, oh, both of these tens place are the same. So the hearts match up. But when you look at the tens place for the first consecutive number and the tens place for the second consecutive number, third consecutive number, you see that they're not matching because this one is 2 and this one is 1. Something you can also tell by looking at this is that it has to be in this kind of order. Like, it has to be the last number of, like, the 20s with the two first numbers of the 30s, or the last number of the 30s with the first two numbers of the 40s, because that's the only way that this will work for the tens place. So let's try another one. When we're looking at this, we also can figure out that the only value that you could get for the square would be 1, right? So that means this should also be 1. So let's start off there. We'll do 19, 20, and 21. So when we're looking at these, we can see that the hearts match up and the squares also match up. And then your diamond would be a 9, and your 0 would be a triangle. So the 9 is a diamond and the 0 is a triangle. And what it asks is, what does Francesca's next number look like? So if we're going off of this, the next number needs to be 22. So we know what 2 looks like. 2 is a heart. So if there's 2 2s in a row, that means it would look like heart, heart. So your answer would be this. And out of all the options, C is the one that has 2 hearts. So the answer is C. Number 12. So I'm going to change this question around a little bit. Let's say Harry Potter has a terrace covered with different square tiles of different sizes. The smallest tile has a perimeter of 80 centimeters. A snake lay down along the edge of the tiles. How long is the snake? So we know that Harry Potter has a smallest tile with a perimeter of 80 centimeters. And to find the perimeter, since it's a square, we know all the sides are the same. So 4 sides have the same exact value, which will equal 80. So for this thing, what you would do is you would try to figure out 80 divided by 4. And to find that out, 80 divided by 4 is 20. So we know that one side of this tile would be 20. So we have one side here, so that's 20 over here. We have 20 over here. We have 20 over here. And then we have this big square. So since we know they're all square tiles, this means that all the sides have to be the exact same. And we see that 3 of the small squares are the same as a large square. So for this, we would need to do 20 plus 20 plus 20 for one side, which would be 60. So we have 60 for this side. And then it goes down, so 60 over here. And then we have this slightly smaller square. It's like a medium-sized square. So for this square, we need to figure it out too. And we see that there's 2 small squares here. So if there's 2 small squares, that means one side of this square would be 40, because 20 plus 20 is 40. And then there's a 40 over here, down here, to the side, up here. And then it goes back down, but only a small square down. So that would be a 20, and then there's a 20 over here. And then we would have to add all of those up. So 60 plus 40 is 100, plus another 60 plus 40 is another 100, plus 40 plus 40 is 80, plus 20 is another 100, and then we get 20 plus 20 plus 20 plus 20 is 20 plus 20, 40, plus 20, 60, plus 20, 80, and then we have another 40. So that would be 120. So plus 120. Then when we all add all of these up, we get 420 centimeters. So the answer for this question would be C. 13. The picture of a digital watch can be seen in the mirror. Which picture of the watch can be seen in the mirror 30 minutes later? So we can know that this watch is seen in a mirror, which means we need to completely flip this picture. So this is the flipped version. We're going to start with this number because it's completely flipped. So let's just draw it like that. So this would be this flipped version of the 5. And then let's move on to the 1. The 1 stays the same because it's basically the same. It just changes sides. And then there's the 2. When we draw it this time, it's actually a 5. And then the 1 at the end is the same. And then we would look at the different options. Okay, so it says that the mirror is 30 minutes later. So this is 21:51. So if this is a 24-hour clock, let's say 9 minutes pass. So 30 minus 9, which is 21. So if 9 minutes pass from this time, then the time that we would see is like this. It would be 22:00, right? But then 21 minutes more have to pass. So the final answer would look like 22:21. But how would that look when it's flipped? Because we're still looking at it in the mirror. So when we flip this whole thing, it would look like this. So we would start with this side, just like how we started for this one. Okay. We would start with the 1, because that stays the same. For this side, we would see that the 5 looks like a 5 like that. And then we have 2 more 2's. So we have 2 more 5 looking shapes. And this is how it would look like after 30 minutes passed in the mirror. So we're going to look at all of our options, and the one option that does fit is D. So our answer is D. Number 14. Maria, Peter, Richard, and Tina play football in the classroom. While doing so, a window pane broke. The headmistress wanted to find out who broke the window pane, and she got the following answers. Maria said it was Peter. Peter said it was Richard. Richard said it wasn't me, and Tina said it wasn't me. It later became clear that only one child spoke the truth. Who broke the window pane? So what we first need to find out is which child spoke the truth. So Maria said that it was Peter. And then Peter said that it was Richard. So one of these people might be is speaking lies, or maybe both of them are speaking lies. And then Richard said it wasn't me, and then Tina said it wasn't me. So who broke the window pane? So the two things that mainly correlate with each other is Peter saying that it was Richard and Richard saying that it wasn't me. So if it was Richard, that means Peter was talking about the truth, Richard was lying, Tina was saying the truth. That means two kids were saying the truth. So it can't be Richard. So let's write. So that's the M for Maria, Peter, Richard, it's R, and then T for Tina. So if it was Richard, two people would be speaking the truth. So it's not Richard. Let's move on to Peter. Let's say it was Peter. Okay, so if Peter was the culprit, then when Maria said it was Peter, Maria's telling the truth. What if Peter said it was Richard? That means Peter would be telling a lie. If Richard said it wasn't me, then Richard is saying the truth. So two people are saying the truth, which means it can't be Peter. So Peter is also out of the game. Let's go to Maria. So Maria said that it was Peter. That means she's telling a lie. So Peter said it was Richard. That means Peter's also telling a lie. Richard said it wasn't me, so Richard would be the one speaking the truth. And then Tina said it wasn't me, which means there's two people speaking the truth. But we know that only one child spoke the truth. So it can't be Maria. That means with these three options canceled out, it must be Tina. But there's also an option that says it cannot be determined. So let's see if Tina is the culprit. If it's not, then it can't be determined. So if Tina was the culprit and Maria said that it was Peter, Maria would be lying. If Peter said it was Richard, then Peter was also lying. If Richard said it wasn't me, then Richard would be speaking the truth. And then if Tina said it wasn't me, then Tina would be lying. So Richard would be the only one speaking the truth. That means that Tina is the only one that would be able to break the window if only one child said the truth. So the answer for this question is B, Tina. 15. Which two tiles should be used to complete the puzzle? So this problem is really similar to the problem that we did before with the hexagon. So I'm not going to go over it that much, but basically what you would do is you would try out all of these different tiles and you would see that 2 and 4 work out pretty well. 2 would work out right here, and 4 would fit in nicely with 2 right over here. And the answer to this problem would be D, 2 and 4. The big rectangle is made up of 5 small rectangles. Lucas wants to color in small rectangles in red, blue, and yellow. 2 rectangles next to each other should be colored in different colors. How many ways are there for Lucas to do that? So we're going to use the 3 colors red, blue, and yellow. We have red over here, we have blue right here, and then we have yellow right here. And these are our 3 colors. So for our first combination, we can put red in the center, and we would put blue over here and blue over here, so they're not touching. And then we would use yellow, put yellow over here, and yellow over here. And this would be our first combination. So let's put a tally mark for that. So that's our first combination, and then we're going to try another combination. Our second combination would be, we're still going to keep red over here, and then we're going to switch the blue and the yellow. So we're going to put blue over here, and then we're going to put yellow over here and over here. And that's our second combination. Let's put another tally mark. Okay. Now we need to go to our third combination. For our third combination, we would put blue in the center this time. So blue is right over here, and then we would have red over here, and red over here, and then we would have yellow over here and yellow over here. So that would be our third combination. And then let's go to the next one. We would have blue still in the center, and then we would just switch the sides for the red. So we would have red over here, and then we would have yellow over here and yellow over here. So that's our fourth combination. And then for our fifth one, we would put yellow in the center this time. So with yellow in the center, we would get yellow, put that in the center. we would have red on two opposite sides, and then we would also have blue on two opposite sides, and that would be our fifth combination. Oop, not the eraser. Our fifth combination. And then our last combination would be just interchanging the blues and the reds. So let's take blue, and we would put blue over here, and then put red over here and red over here. And that would be our sixth combination. And overall, we would have 6 combinations, which means our answer would be D. 17. In a game, one is allowed to take some or all building blocks from the top of a stack of building blocks, turn them upside down, and place them back in the same position with one move. See the diagram. Grand starts with this building block. In the end, all building blocks should be ordered according to size like this. So kind of like this. Okay. What is the minimum number of moves Goran needs to make? So let's try and figure this out. So we have the blocks looking like this at the start. So what you would do at first is you need to try and get this big block at the bottom. But the easiest way to start this off is by switching this top 2 blocks. So it would look kind of like this. So this is the really big block, this is a really small block, and then we have the slightly bigger block, and then we have the slightly bigger block. So at first, it would look like this. So that's move number 1. So you already used it one move. Okay. And then you would flip over this entire structure to get this large block on the bottom. So our structure would then look kind of like this. This is a really big block. This is a really small block. Our slightly bigger block. Oh, that's a really skinny block. Let's make it a bit chunkier. And then our slightly bigger block. So it would look like this. And then from here, all you need to do, and that takes up another step. So that's step number 2. But it's still not in the right position. So A is definitely not an answer. So now all you need to do is just flip this small part to get it to the shape that we want. So once we flip it, you get the really big block, slightly smaller block, and the smallest block. And it would look like this. So that only took us 3 moves. So the answer to this question is B, 3 moves. Number 18. A rabbit, a beaver, and a kangaroo are having a competition. All 3 begin at the same time from the start and hop in the same direction. The beaver always moves 1 position forwards in each jump. The rabbit always moves 2 positions forward in each jump, and the kangaroo always moves 3 positions in one jump. Whoever takes the least amount of jumps to land exactly on the position labeled Zeal, so exactly on that position, is the winner. Who wins this competition? So let's assign colors. So the beaver will be yellow, our rabbit will be green, and then our kangaroo will be blue. Let's start with our beaver. So our beaver always moves in 1 position forwards for each jump. So we see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So Beaver takes 11 jumps to get to where he needs to go. So let's put that down, 11, okay? And now we're going to try the rabbit. The rabbit always hops twice. So you get 1 and 2. So that's 1 jump, 2 jump, 3 jump, 4 jump, 5 jump, 6, 7, 8, 9, 10, 11, 12, 13, 14. And if you can tell that it's never going to land on the zeal. So we can't count the rabbit. So a rabbit would have literally an infinity number of jumps and still not get there. So let's look at the kangaroo. The kangaroo has 3 per jump. So that's 1, 2, 3 in 1 jump. So 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So the kangaroo also gets there in 11 jumps. So something that's similar with the kangaroo and the beaver is 11 jumps. So they both get there at the same exact time. And when we look at our options, we see that E says the kangaroo and beaver will both be the winner. So the answer to this question is E. Number 19. So let's say Olivia, my friend, wants to have the sum of all the white squares equal to sum of all the black squares. But the thing is, that's not working out right now. So which two numbers have to be swapped so the sums are equally as big? So for this one, we're just going to do guess and check. So right now, let's see what the total of each square is. So 2 plus 6, 6 plus 4 is 10. 6 plus 4 is 10. 10 plus 7, 17. 18, 19, 20. So all the black squares have 20, the black squares. And then all the white squares are, let's see, we have 11 plus 13, which is, 24. 24 plus 5, which is 29. 30, 31, 32, plus 8, which is 40. So the sum of the white squares is almost double that of the black squares. So we need to meet somewhere in the middle. Let's see. So for A, it says to use 1 and 11. So 11 is currently a white square, and the black square is currently 1. So we would subtract 1 from black, which would be 19, and then add 11. So that would be, so if we subtracted 1 from black, that would be 19. 19 plus 11 would be 30. Okay. Now for the white squares. For the white squares, we would have to subtract 11. Subtracting 11 would be 29. So subtracting 11 would be 29, and then we would have to add 1 because that's what we're switching over, plus 1. And that would equal 30. So we can see that both the black squares and the white squares have both 30 if we just switch 1 and 11. So the answer for number 19 would be A. Number 20. The gear marked A is turning clockwise as shown. Which two boxes will move upwards? So this is with gears, and you have to really draw this out to make this much easier to solve. So this A gear is moving clockwise, and it's hitting this gear. So when it hits this gear, it moves this gear kind of like that, so in like this direction. Okay? And since this gear is connected to this gear, if this one is moving in this direction, then that means that this gear is also moving in this direction. So they're both moving in the same direction. But let's start with this gear, which is touching this gear. So when this gear, the smaller gear is moving in that direction, this pushes this gear to go kind of like that. If it's moving in that direction, that means this one is getting longer, which causes 1 to drop down. And since 2 is on the other side, this causes 2 to move like that, which means 2 is moving up. And what this question asks is which two boxes will move upwards. So 2 is definitely one of them. Okay, now let's go over here. So when you see this gear is moving like this, the smaller gear, we can kind of see that this gear would be moving in like almost like a this way fashion. So kind of like that. It'd be moving that way, right? And then if it's moving that way, we see how it pushes the smaller gear over here to move like that. So if you follow the movement, we can see that 4 would start going down, and then also following the movement this way going up, we see that 3 goes up. So 3 is another box that goes up. And as we look at our solutions, we see that B says that both boxes 2 and 3 will be moving upwards. Question number 21. Tina draws shapes in each field of the pyramid. Each field in the second and third row contain exactly the shapes of the 2 fields below. Some fields are already done. Which shapes does she draw in the empty field of the bottom row? So, for this question, we know that the fields below every other field has the 2's that are hitting it. So, this field would fill this one and this one. This field would have this one and this one. So, by looking at all of this, we need to find some criteria that the bottom field must hit in order for the top field to look like that. So, something that I figured out is that we can only have one square in all 3 bottom rows. So, in the middle row, we can have no squares. So, no squares. So this is how I figured it out. And the top, we see that there's only one square. And then when we look at the bottom row, we see that there is also only one square. So if we added another square into the middle square, that means it would make 2 squares, and that would not be the right answer. So we don't have any squares in the middle. So let's look at our options, which means it wouldn't be A, but all the other ones could possibly be true. Okay, now let's move on to the triangles. So we see that there are 2 triangles in this one right here. So when we look at the bottom 2 squares that are already filled in, there's no triangles. So we understand that there is at least one triangle that we need in the middle square. That's because if there's one triangle in this square, that means there's one triangle here and one triangle here. And then one triangle plus one triangle means that there will be 2 triangles here. So we need exactly one triangle, not 2, 1. So when we look back into our options, we see that it can't be C. And all the other ones could possibly work. And then we move on to the number of circles. So for this one, it needs to be 1 circle in the middle square. So how I know that is that there's 4 circles on the top. So we have 1 circle here, and we have 1 circle on the other side. So to make sure we get 4 circles, we could put 1 circle over here, and you get 2 circles right here, and 2 circles right here, because of the 2 ones that hit that square. And then at the top, we get 4 circles. So we know there needs to be only 1 circle. So we look back at our options, and the only one that fits all of our criteria is D. So the answer to this question is D. Number 22. Martha chooses one of the 5 structures below and combines it with the structure on the right. The table below shows the number of cubes in each column and the combined structure as seen from above. Which of the 5 structures did Martha choose? So the structure on the right that they're talking about is this structure right here. And this problem is really similar to 2 other problems that we did before, where we had to match 2 structures together to make sure that it fit like a certain pattern. So from all these structures, we would look at them and we would try them out one by one. And we would eventually see that D would work best. So over here, we already have the 3, so that fills up this square. So we're done with that. Over here, we can see that there's 2, so that fills up this square. So what it's missing is 3, and this one provides the 3. So we figure out this square. And then we need 2 in this square, which is covered right over here. So we're good with that. And then we need 1 in the middle right over here. So this gives that 1, which is covered. And then we need 2, which is right over here on the picture on the right, which is covered. And then we have 1 over here that's covered. There's nothing that we need in the bottom. And then we have 1 over here that's covered. So D is the correct answer. Number 23. There are two machines. Machine R rotates the paper 90 degrees clockwise. Machine S stamps the paper with a cute-looking clover symbol. In which order were the machines used to create the images shown below? Okay, so for this one, we're just gonna guess and check. So if the image was first stamped on the first one and then turned, so we would see an image kind of like 1, 2, 3, right? And that's when it was stamped. And then the next one, it would be turned. So it would look kind of like this. And then it would be turned again. And then it would be turned one last time. But that's not the same as what we're trying to get. So it's not A. Whee. It can't be A. Okay, let's look at B. So what the first thing you do is you rotate it. But even if you rotate it, nothing's really going to happen because there's nothing on the paper yet. So we don't really count that step. And then we would stamp it. So when we stamp it, it would look like this cute little clover. And then we would turn it once over here. And then we would turn it again. Like that. And that is very similar to the image. So we know that the answer will be B for this problem because when we do the steps, it looks exactly like what is shown. Number 24. 4 posts are placed along a 120-meter long running track. How many more posts have to be placed so that the running track is split into equally long sections that way? So we see that the running track is already split up into 3 sections. And there is the 24-meter one, the 30-meter one, and the 66-meter one. And now we have to evenly split all of them to make sure that the entire track is evenly split up. So for this one, let's see what the greatest common multiple is for all 3 of these numbers so we can find something that would be pretty big that we could split up into. So some of their similar multiples would be, it could be 2, 3, 6, and I can't really see any other ones. So we're going to use the greatest one, which is 6 right now. So we want to split the entire 120-meter long running track in 6. So we would do 120 divided by 6, and when we do that, we get 20. So we're trying to divide this running track by 20, but we already have 4 posts down. So what would we need to add to get 20 posts? You're thinking 16, right? But one of these posts just like mark the start of the trackway. So we don't totally count that post. So we would do these 3 posts plus what number is equal to 120 or is equal to 20. So 20 minus 3 is 17. So 3 plus 17 would equal 20. So to evenly split up all of these different sections, we would need 17 poles to make sure that we could equally split them up, the 120-meter long running track. So the answer for this question is C. So we have finally reached number 25, which is one of the last 5 of the questions in the Math Kangaroo. So the last 10 questions are 5 points. And especially the last 5 questions are probably going to be the most challenging just because they're probably going to take the longest amount of time and they're generally at the end of the test. So you really need to make sure that you have all your brain power to work on these problems. So let's get started with number 25. A tower is made up of bricks that are labeled from numbers 1 to 50 from bottom to top. Bob uses the bricks to build a new tower. Each time he takes 2 of the topmost bricks off the old tower and places them down on top of the new tower without changing their order. So basically what he does is that there's going to be a tower over here and there's the top 2 bricks. Instead of changing the order back to like 50 and then 49, he just takes them like how they are and places them down on their new tower. Okay, which two bricks lie on top of each other when he's finished and with the rearrangement? So for this question, you can't always assume that two adjacent numbers or two consecutive numbers, which means numbers right after each other, are together. So when you look at 29 and 28, you can't always assume that 29 and 28 are going to be together, because in this one, some of them are together, but at the same time, some of them are not. So 29 and 28. So I wrote these numbers down, and let's find 29. 29 is right here, and 28 is right here. So they're definitely not even touching. So I don't think it would be A. Okay, B, which is 34 and 35. So for this one, it's the same concept as A, why A doesn't work. So 35 is down here, 34 is up here, and it won't be B. So we see C, which is 29 and 26. Technically, there's a very real possibility that this could totally work, but 29 is all the way down here, and 26 all the way up here. So it's definitely not 29 and 26. So I feel like the easiest way to do this problem would just be to write down the numbers. It's really easy if you just follow the pattern. So for D, it's 31 and 33. Let's see where 31 is. 31 is right here, and 33 is right here. It's only split by one number, but still it's not right next to each other, so it can't be D. And then we get 27 and 30. So where's 27? 27 is right here, and 30 is right here. So these two numbers are right next to each other, which means the answer for this problem would be E. Number 26. Martin has 3 cards with numbers written on both sides. The card with the number 1 has the number 4 on the opposite side, the card with the number 2 has 5 on the opposite side, and the card with 3 has 6 on the opposite side. Martin randomly places all 3 cards on the table and adds up the 3 numbers he sees. How many different sums can Martin get? So for this problem, let's write down all the possible ways that the cards could be arranged. So one way is that there would be 1, and then these 2 would be flipped, so 5 and 6. And then we could have 1, and 2 of them would have the front side, and then 1 of them would have the back side. And then we have 1, 2, 3, where all of them have the front side. And then we could have the 1 flip over. We could have 4, and then we could have the back side of the second card and third card. And then we could have 4, 5, 3. And then we could have 4, 2, and 3. So we're going to add all of these ups to see how many sums we get. So 6 plus 5 plus 1 is 12. 6 plus 2 plus 1 is 9. 3 plus 2 plus 1 is 6. 6 plus 5 is 11, plus 4 is 15, I believe. Yep. And 3 plus 5, 8. 8 plus 4, 12. And then 3 plus 2, 5. 5 plus 4 is 9. So let's match up the sums that are the same. So 12 and 12 are the same sum, and 9 and 9 are the same sum. And then we have 1 of 15 and 1 of 6. So let's count them all up. We have 1, 2, 3, 4 different sums. So for this question, the answer would be B, which is 4 different sums. Number 27. In a second-hand store, 2 hats are sold for the same price as 5 skirts. 3 skirts are sold for the same price as 8 t-shirts, and 2 t-shirts are sold for the same price as 3 caps. Which of the following collections are the most valuable? So the easiest way to solve this question is that we would start assigning values. So 2 hats are sold for the same price as 5 skirts. Let's find a nice even value that would easily divide both into 2 and 5. I'm going to choose the number 20. So if it's 20, that would mean that 1 hat, H for hat, would equal 10, and 2 hats are sold for the same price as 5 skirts. So 10 plus 10 is 20, and the 20 divided by 5 for the skirts, S is a skirt, would be 4. So each skirt is $4. And then 3 skirts are sold for the same price as 8 t-shirts. So if you have 3 skirts, you have $12, and you would have to divide that by 8. So if you did 12 divided by 8, you could simplify that by 4. And then you get 3 divided by 2, which is the same as 1.5. So t-shirts, I'm going to put that as a T, is equal to $1.5. And then 2 t-shirts are sold for the same price as 3 caps. So 1.5 plus 1.5 is 3, and it's sold for the same price as 3 caps. So that would mean that 1 cap equals $1. Great, so we assign dollar values. This was just some math. So we can clearly see all our different values, and now we gotta add them all up and see which one works. So A has 1 hat and 5 skirts. So 1 hat is $10, 5 skirts is $20. So that would mean A would give you $30. For B, you have a hat, 3 skirts, and a cap. So for each skirt, that's 12. It's 12. I'm going to put that right here. There's 1 hat, which is 10. And then we have 1 cap, which is 1. So that would be 10 plus 12, which is 22, plus 1 is 23. Okay, equals 23. Now let's go on to C, which is 8 skirts and 6 t-shirts. So each skirt is 4 times 8, which is 32. 32. And the t-shirts, 6 t-shirts times 1.5. So let's do some quick math. 1.5 times 6 is equal to 9. So you have 9 there. And that would be 32 plus 9 is 41. Yeah. And then you have 37 caps. Well, each cap is $1. So when you assign that value, it would just be 37. And then 3 skirts and 3 caps. 3 caps, that's $3. Let's put that right there. Oh. And then the 3 skirts, each skirt is $4, so that's $12-ish, which would equal 15. So out of all of these, the one that costs like the most money and is the most valuable is C at $41. So the answer to this question would be C. Robert and Sonja are playing a game with the following rules. Taking a turn, they can take 1, 2, 3, 4, or 5 cards from each pile on the move. Whoever takes the last card has lost. At the moment when there are 10 cards on the pile and it is Robert's turn, how many cards should he leave for Sonja so that he can be certain to win? So, for this one, we need to understand that if Robert takes 1, 2, 3, or 4 tiles, then Sonja can win by taking the remaining amount of tiles. But if they take 5 tiles, then Sonja can win by taking a little less and then forcing Robert to take the rest amount of tiles. So it can't be 5 tiles because then that would let Sonja to win. So for this one, what we would do is we would look at it. So if there are 8 or more tiles left, then we could have Robert take some amount of tiles that leaves 8 or more tiles left, and then Sonja would take some tiles, a little amount of tiles, maybe like 4-ish tiles, and that would force Robert to take the remaining amount of tiles so that he would lose. So it can't be either one of these. And then when we look at both of these, what we would do is, so C is that they would take 3 away, and then D is that he would take 4 away. And the most easiest way to win would most probably be C, because it allows for a greater possibility that Robert would be able to win just because of all the different combinations that you could do on how many tiles you could take. So the answer for number 28 would be C. Number 29. Which of the following four shapes has the greatest area? So let's figure out the area. So they're all part of like 2x2 squares. So they all have like a base area of 4 before their shape. And then let's start with the W. So they have a base area of 4x4, and then we're gonna try to figure out the area of this triangle right here. So it spans, the base is 2, the height is 1, so 2 times 1 is 2, and then you would divide that by 2 to get the area. So that would be 1, so you subtract 4 by 1 to get 3, and then we're going to add these two together. So both of those are 1 by 1 triangles, and then you divide by 2 to find the area, so both of them would have an area of a half. A half plus a half is 1, so you do 3 minus 1 is equal to 2. So the area of W is 2. I'll write that right there. Okay, now for the diamond. So this diamond, what I'm going to do is I'm going to have these 4 triangles that are cut off right here, 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 and here. So those are all 1 by 1 triangles. So 1 times 1 is 1, and then you would divide by 2 to get the area, which is a half. So a half plus a half is 1, and a half plus a half is another 1. So 1 plus 1 is 2. So it has a base area of 4, and then you subtract by 2, and you get 2. And then let's now go over to the crown. So the crown also has a starting area of 4. Write that down, 4. And let's cut out all of the triangles. So we have 2 triangles, one right here and one right here. The triangle is 2 by 1, and 2 by 1 is a base times height, which is 2 times 1, which is 2, and then to find the area, you have to divide by 2, and that would make it 1, and then there's 2 of them, so 1 plus 1 is 2, so we subtract that by 2, and we get 2 as area. And then for lightning, it still has a starting base of 4, and then we cut out this 1 by 1 triangle, these 4 1 by 1 triangles. So 1 by 1 triangles have an area of a half. So a half plus a half plus a half plus a half would be 2. So you would subtract by 2 and you get 2. So all of these have the answer 2, 2, 2, and 2. So the answer to this question would be E. They all have the same area. Number 30, our last problem. An explorer wants to find a path through the maze shown from the point marked from start to the point marked finish. She can only move horizontally and vertically, and she can only pass through the white circles once. She also has to pass through all the white circles, and she cannot pass through any of the black circles. When she reaches the circle marked X, what will her next move be? Okay, so let's start from the starting point. We start right here, and we're moving this way. So we're just going to see how we can navigate this maze while also following everything that they say. Oh, I think I did something wrong. Okay, let's backtrack a little bit to right about here. Oh. And I think I move across like that. Yeah, there we go. And then like this. And I got to the very end without hitting a single black circle and entering all the white circles only once. So the circle that we're going to look at is the one that has the marked X. So we see how we move. So we moved to the side over here, and then we moved down right here, moved to the side, hitting the X thing, and at the X marked circle, we move down. So when we look at all of our options, B shows the moving down part, so the answer for this question would be B. Thank you.
Don't forget to subscribe and like. If you have any questions, you can email info@agoramatrical.org or comment below and we'll reply back. Maybe. And if you want to see practice things or anything about us, you can visit our website, which is basically the end of the email but without the info and the end. So bye!